Okay, in this example, we find the parametric equations of the tangent line for the vector-valued function r of t equals t squared minus 1 for the first component, t squared plus 1 for the second component, t plus 1 for the third component, at the point negative 1, 1, 1. So it's important to realize what we're given here. This r of t graphs to be a curve in space. And this point right here, we're saying, is a point on that curve. So there should be a t value you can plug in here that will generate this point, which is really the tip of one of the arrows that you get for a particular value of t when you plug it in the vector valued function. Okay, well, hopefully it's obvious that t equals 0 will produce this point. If you plug in 0, you'll get negative 1, which matches up with this, negative 1. If you plug in 0 here in the second component, you'll get the second coordinate of 1. And if you plug in 0 here, you'll get the third component. Over here, the component will be 1, but we're going to think of it as the tip of the arrow is just a point on the curve, and so the third coordinate is 1. So t equals 0 produces this point on the curve given by r of t. If it weren't obvious, you could set one of these components equal to the appropriate coordinate and solve for t that way, hopefully, right? Okay, so we want to find the parametric equations of the tangent line at this point. So we need a direction vector. Think about what we need to do to find the parametric equations of a line. We need a direction vector, which is going to be the tangent vector, the direction vector. For the line in this case, for the parametric equations of the line, the direction vector is going to equal a tangent vector. Any scalar multiple of the tangent vector would do. So it's not a tangent vector. It's not the tangent vector, rather, it's a tangent vector. Okay, so let's find r prime of t. R prime of t you can get by taking the derivative of each component of your vector valued function. So hopefully you can see that that's going to be 2t, 2t, and 1. If you take those derivatives. 2t, 2t, and 1. But we're really only interested in the tangent vector at t equals 0. So let's find that. R prime of 0. And if you plug in 0 for t, you get 0 here for the first component, 0 here, and 1 here. So this is our direction vector when t equals 0. This is the direction vector. Okay. Then we remember to find the parametric equations of the line, we need a direction vector and we need a point on the line, but the point is the one given. Negative 1, 1, 1. So the point, our point on the line would be negative 1, 1, 1. So just to remind you, the parametric equations of the line, they're given by x equals x naught plus at, y equals y naught plus bt, and z equals z naught plus ct, where x naught, y naught, z naught is a point on the line, so this is our x naught, y naught, z naught up here for this point, and a, b, c would be the components of the direction vector. So let's fill it in. We get x is equal to negative 1 plus 0t. Y is equal to positive 1 plus 0t. And z is equal to z naught, which is 1 plus ct, so c is 1. So 1 plus ct. Whoops, sorry. 1 plus t. There they are. So if you were to draw a picture, I don't know what R of t looks like, but let me just kind of give you a general idea. If this is some R of t, and let's say you wanted the tangent line at this point, then essentially what we did was we just found the parametric equations that would produce a line that looks like that.